Thank you so much. Good morning, everyone. My name is Deepro Banerjee, and I'm from the Graduate School of Science and Engineering at Soka University in Japan. And I'll be presenting on the topic of Hetero-Core fiber optic glucose sensor that has been coated with glucose oxidase, immobilized in a pH-sensitive polymer multilayer made up of two polymers, which are Poly-L-Lysine and polyacrylic acid. So this is the overview of my presentation today. I'll first introduce a few related topics for my presentation. Then I'll move on to discussing about the proposed sensor device before explaining the experimental setup, showing you the experimental results, and then finally concluding the presentation. So let's first move on to introduction. So glucose sensing. So at first, glucose, it's the most abundant monosaccharide in nature. This is the chemical structure of glucose. And the monitoring of glucose is important in different fields, such as food and beverage, agriculture, environmental monitoring, and maybe the most well-known and the most widely used in the field of healthcare, in monitoring diabetes. Diabetes is a chronic illness that causes an increase in the blood sugar level of its patients, and diabetic patients have doubled in the last 20 years. This is a map that shows the prevalence of diabetes in 2021. So a lot of countries in red, so the number of diabetic cases are rising, so proper monitoring of diabetes is needed. And the World Health Organization estimates that there will be around 700 million diabetics by the year of 2045. So currently, the glucose sensing is mainly for healthcare is mainly done using these following methods, which are blood glucose monitoring, continuous glucose monitoring, both of which are invasive in nature and a nightmare for people with trypanophobia, which is the fear of needles. There are non-invasive methods, which are, urinalysis strips, but urinalysis strips are use and throw, so it's often very unsustainable. And there's research regarding, glucose sensors based on semiconductors and optical fibers and other optics-based sensors. So my research is also based on this one of these, technologies, which is optical fiber sensor. And my lab specifically uses Hetero-Core optical fiber, and this is what the Hetero-Core optical fiber looks like. It's, as the name suggests, it's made up of different core diameters, and so as to deliberately let the light leak into the cladding, and thus the amount of light that gets reflected back into the downstream transmission line is depending on the refractive index of this of the surrounding medium. So why optical fiber? Because optical fibers have some really advantageous properties, such as being electromagnetic interference immune, being corrosion resistant, among many other advantages. And Hetero-Core optical fiber, when compared to other optical fiber sensors, are mechanically robust, has an easy fabrication process. So it's the one that I chose for my research. So now let me talk about my proposed sensor device. So this is the device structure, and it's made up of a 50 micrometer, 3 micrometer, 50 micrometer configuration of Hetero-Core optical fiber. And the Hetero-Core portion has been then coated with a polymer multilayer of Poly-L-Lysine and polyacrylic acid. So for this experiment, we've made 10 layers of this multilayer. And then on top of this polymer multilayer, we have immobilized glucose oxidase, which is an enzyme that reacts with glucose to act as the glucose sensing layer. So now let me talk about the working principle briefly. So in presence of glucose, this enzyme glucose oxidase, this reacts with glucose and forms this acidic product, which is D-gluconic acid. And D-gluconic acid, being an acidic product, it changes the pH of the surrounding medium. So as the pH of the surrounding medium changes, there's a swelling and shrinking of the polymer multilayer of Poly-L-Lysine and polyacrylic acid. So this swelling and shrinking in turn changes the refractive index of the surrounding medium, and that's how the Hetero-Core fiber senses the change of refractive index, and thus changes thus the sensing is done. The materials that have been used in my case are these two polymers of poly-L-Lysine, polyacrylic acid, and the polyacrylic acid, of course, has the COOH group, and the COOH group forms a COO minus, and then the poly-L-Lysine forms a NH3 plus. So this minus and plus, they electrostatically, interact with each other and form multi-layers. And the glucose sensing layer was, so glucose oxidase was immobilized using this N-hydroxysuccinamide and carbodiamide, which is often used to immobilize large biomolecules in polymer layers. A quick look at the fabrication process. So heterocore optical fiber is usually fabricated using cleaving and fusion splicing. The polymer multi-layers are fabricated using the layer-by-layer technique, and the glucose oxidase layer, as I just mentioned, is immobilized using NHS-EDC solutions. So let me give you a quick look at the the layer-by-layer technique. So layer-by-layer technique is often used to deposit these polymer multi-layers, and it's a technique that takes advantage of oppositely charged materials. So let's take an example. This is the fiber cladding. So once we make a layer of polycation on top of this fiber cladding, since the polycation is positively charged, then once the polyanion, which is negatively charged, is deposited on top, they electrostatically interact with each other, and they form self-assembling polymer multi-layers. So that's how the polymer layers are made. All right, let's take a look at the experimental setup. The experimental setup is rather simple. This is the optical fiber sensor, and one side of the optical fiber sensor is connected to a white light source of 400 to 1600 nanometer wavelength. It's also connected to a spectrometer of 400 to 1000 nanometer, and then there's a PC for recording the spectrum. The conditions are the temperature of the environment was kept at around 25 degrees centigrade and the humidity at around 40 to 50%. So that's all about the experimental experimental setup. So let me move on to the experimental results. So I'll first show you the layer by layer technique results. So this is the normalized light intensity versus wavelength graph for the layer by layer experiment. And we can see that with an increasing number of layers, the normalized light intensity decreased. So this indicates there was an increase in absorption, which indicates that the effective refractive index of the polymer layers increased, and thus we can say that the polymer layers were being successfully formed as the effective refractive index had increased. So now if we move on to the glucose sensing experimental results, we can see from this normalized light intensity versus wavelength graph that there was a gradual decrease in the normalized light intensity with an increase in the glucose concentrations. So in this experiment, I have chosen two sensing wavelengths at 650 nanometer and 850 nanometer. So 650 nanometer is the wavelength of red LED, which can be used as a cheap source of light, thinking about practical usage. And 850 nanometer is commonly used in optical communication. So that my sensor can also take advantage of the existing setup, so that it's way more viable for practical applications. So we check the spectrum at these two sensing wavelengths, and this is the optical loss versus glucose percentage graph at 650 nanometer and 850 nanometer. And we can see that the optical loss had increased with the increase in the glucose concentrations. So at 650 nanometer, the 10-layer sensor had a sensitivity of 0.0782 decibels per person, and at 850 nanometer of around 0.0505 decibel per person. We could see that the sensitivity was higher for that of 650 nanometer than that of 850 nanometer, and that can be explained by previous research, which shows that the Poly-L-Lysine and polyacrylic acid polymer complex has a inherent absorption peak at around 450 nanometer. So 650 nanometer being closer to 450 nanometer has a higher sensitivity in this case. So that was all about the uh, experimental results. Let me move on to the conclusion. So we saw from my presentation that glucose monitoring is a essential parameter to be monitored in several industries, food and beverage, and mainly healthcare. And so my research deals with the development of a glucose sensor using Hetero-Core optical fiber that has a pH-sensitive polymer multilayer. And the pH-sensitive polymer multilayer was fabricated using this layer-by-layer technique. And the pH change occurred on the formation of gluconic acid when the glucose oxidase reacted with the glucose, and thereby there was a change in pH and thereby a change in refractive index. And the glucose sensor that has the multiple layers of poly-L-lysine and polyacrylic acid pair, it could differentiate the solutions of 5% to 25% glucose solutions with a maximum sensitivity of 0.0782 decibels per person. And so in conclusion, we can say that the study has been successful in developing a novel glucose sensor using Hetero-Core optical fiber that is based on pH change. So that is all from my side, and now I'm open to questions. Thank you.